This is Chapter 2, Matter and Minerals for Earth Science 100, Waubonsie Community College. In Chapter 2, we're going to be looking at several learning objectives. The first is to list the main characteristics that an earth material must possess to be considered a mineral and describe each characteristic. The second is to compare and contrast the three primary particles contained in atoms. The third is to distinguish among ionic bonds, covalent bonds, and metallic bonds. And the fourth is to list and describe the properties used in mineral identification. The fifth objective is to list the common silicate and non-silicate materials and describe what characterizes each group. And the sixth objective is to discuss Earth's mineral resources in terms of renewability, and to differentiate between mineral resources and ore deposits. In Section 1, we look at the definition of a mineral, which has several characteristics. The first is that it's naturally occurring. The second is that it's inorganic. The third is that it's a solid. The fourth is that it possesses an orderly internal structure of atoms. And the last characteristic is that it has a definite chemical composition. Now, a rock could be one or more minerals combined into a solid mass. So any naturally occurring solid mass of mineral or mineral-like matter is considered a rock. Here's an example of a rock we call granite, and as you can see, there's at least three different colors within the rock, and those three colors are made up of three minerals. The first, the lighter colored mineral, is called quartz. The very dark or black colored mineral is called hornblende. And the third, the pinkish color, is called feldspar. These are all minerals that make up the rock called granite. And of course, minerals consist of atoms in various arrangements. The smallest particle of matter is called an atom, at least for our purposes. There is a structure to every atom. And of course, the center of every atom, called the nucleus, consists of protons and neutrons. The proton is a particle which has a positive electrical charge. The neutron is a particle which has neutral charge, in other words, no charge. And then surrounding the nucleus is a particle called an electron, which has very little mass and has a negative electrical charge. These are two models of an atom. The top one is one that we... So if we put together a bunch of atoms, we have something which, if they're all the same, would be considered an element. And an element is always defined by its atomic number. The atomic number is just the number of protons in the nucleus, only the number of protons. And that helps to determine its chemical nature. Because it has a positive charge, we would likely then look at the negative charges that hopefully will balance out the element. An element would be something where all the atoms have the same number of protons, and the same atomic number is what they mean. So in other words, if we have an element of lithium, which has an atomic number of 3, then it has 3 protons in every atom. Every atom, of course, has the same chemical and physical properties. So if that's what makes up an element, the element must have those same properties. So how do we represent all of these elements that exist in nature? Well, we use what's called a periodic table. It's a tool used to organize those known elements into actually 92 naturally occurring elements. More have been synthesized, but they're very, very complex and have a very short lifespan because they're so large. The atomic structure can't be held together naturally. Here's a picture of the periodic table. As you can see, element number 1 is hydrogen, which consists of 1 proton and 1 electron. Over on the far right is helium, which has an atomic number of 2. And here we see if the atomic number is 2, there must be 2 protons in the nucleus. And it goes on from there all the way down to element 92, which is the last naturally occurring element. Beyond that, as you can see in the green row down at the bottom, we have things, elements which have higher atomic numbers, but as I said before, those are elements that are artificially produced in the laboratory and fall apart pretty quickly. Atoms bond or stick together in different ways. There are ways in which that elements with electrons in them can actually share or move electrons between or among atoms. And these are the rules that apply to those various sharing capabilities. We're not going to go into a lot of detail here. This might require more of a chemistry course, but we will look at the types of bonds that atoms can have. The first one is called an ionic bond, where you have positively and negatively charged atoms. They're strongly attracted to each other because of their electrical charge. And in some cases, an atom might give up one of its electrons to another atom nearby. One of the most common substances that we have direct contact with is salt, or sodium chloride. And as we can see in the picture here, there's a certain number of electrons in sodium and a certain number in chlorine, which makes up sodium chloride. And they tend to work together to create what you see on the right, which is a fairly stable substance we call salt. So if we were to take a grain of salt or a crystal of salt, we would naturally see this atomic arrangement. And as it turns out, if this is built out to a large scale, we see that salt has cubic crystals, cube-shaped crystals. Then there are covalent bonds, where no ions are present, but we're sharing different electrons within the clouds between two atoms. So the formation of a covalent bond is pretty easy to see here, where electrons are going back and forth between atoms. Metallic bonds are very interesting because there are ions, and those atoms have electrons which are free to move throughout the structure. In other words, electrons can flow, and that's of course the basis on which electricity moves through a wire. So with metallic bonds, there are obviously positively charged particles, negatively charged particles, and of course neutrons, but these electrons can move pretty freely within the substance. Next, we need to look at the properties of minerals, those things that would help us possibly identify the mineral. The first is luster, which is just the appearance of the mineral as seen in reflected light. The color is not a good characteristic but for most minerals, but can be used in certain ones. The streak of the mineral is what you would see if you scraped a little bit of the mineral onto what's called an unglazed porcelain plate or streak plate. It's the color the mineral has in powdered form, and that can vary quite a bit from what you see as far as the color of the mineral. And of course, the ability to transmit light. If the mineral is transparent, of course we can see through it. If it's translucent, it might block some of the light, and of course there's opaque. So crystal shape or habit can also help identify some minerals. On the pictures here, you see the fibrous structure that asbestos would have, a bladed structure, a banded structure, and even cubic crystals, which, as I mentioned before, might be something characteristic of sodium chloride or salt. So these shapes are pretty common among nature. The fibrous one, not so much, but cubic crystals and other shapes can be pretty easily found if you can find the crystalline form of the mineral. There's also the mineral strength. How easily can it break or be deformed? And that's determined by the bonds between the atoms. So the first and most important characteristic would be the hardness of the mineral. As we probably all know, diamond is the hardest mineral naturally found in nature, and a substance like talc, which is a rock, would be considered one of the softest minerals. But there's also ways in which the atoms might be weak in one direction, and that's called cleavage, and that's the tendency to break along those planes of weak bonding. If a mineral does not have cleavage, then it must have fracture, which is a random pattern. But even that random pattern has certain characteristics that we can identify. And another one is called tenacity, which is the resistance to cutting, breaking, bending, or deforming. There's also a characteristic called specific gravity, which is the density of the mineral. Some minerals might have very little weight for the volume it has. Others are very, very heavy for the volume it has. So specific gravity can help identify a mineral. Looking at hardness again, this is a scale called the Mohs scale of hardness, which gives us relative hardness on a scale of 1 to 10. So as I mentioned before, diamond is 10, talc is 1, one of the softest minerals, and then we go up the scale to various numbers. Talc is 1, gypsum is 2, calcite is 3, fluorite is 4, apatite is 5, orthoclase, which is a type of feldspar, is 6, quartz is 7, topaz is 8, and corundum is 9. Now, those are the basic 10 minerals that we can use to classify mineral hardness. The objects on the right are objects that have those hardnesses. So, for example, if we have a glass or a piece of glass or a knife blade and we find that we can scratch the piece of glass, that would mean that the mineral is harder than the piece of glass, which is 5.5. So by using these materials on the right, these common objects, we can sometimes kind of narrow in on the hardness of the actual mineral. Here's a slide which shows different ways in which minerals will cleave. In the upper left here, we see cleaving in one direction, which is typical of muscovite mica, where you can actually peel apart very thin layers of the mineral. Whereas something in the lower right, such as fluorite, has 4 directions of cleavage. And the way to identify those is to find pairs of parallel sides. So regardless of the angle, if you can count the pairs of parallel sides, you can determine the number of cleavage directions. Other properties that minerals might have are things like taste. Sodium chloride would be one obvious example. Smell. A mineral such as sulfur would have a distinctive smell to it. Elasticity, in other words, how bendable it is. Malleability, if you could pound it into a flatter shape, such as the mineral copper, that would be a highly malleable mineral. Double refraction, which would mean the mineral is transparent, but when you look through it, you see double. Some minerals have magnetic properties, so magnetism is a characteristic. How it feels might be distinctive, such as the mineral talc, and how it reacts with hydrochloric acid, which is a distinctive test for a mineral such as calcite. There are various mineral groups that make up rock-forming minerals, and those mineral groups consist of basically these 8 elements: oxygen, silicon, aluminum, iron, calcium, sodium, potassium, and magnesium. These are the basic building blocks of most minerals. This is a pie chart showing the percentages of those elements which exist in the continental crust, and you can easily see that silicon and oxygen make up the majority of it. So if we put silicon and oxygen together, we normally get a silicate mineral. It's the most common mineral group. It obviously contains those 2 elements, silicon and oxygen, and typically those 2 elements combine into a certain crystalline structure called a silicon-oxygen tetrahedron, or just silicon tetrahedron. So typically we might have 4 oxygen atoms surrounding a silicon atom in the middle, and this will combine with other atoms to form various silicate structures. This is a good way to visualize the silicon tetrahedron, again with the larger oxygen atoms surrounding the smaller silicon atom in the middle. So as you can see in your book in much better detail, these are common silicate minerals that we find in nature. Just giving you the first example here, we have a mineral called olivine, which has no cleavage but has a single tetrahedra structure, and you can see a picture of or an example of it over on the right. So these are typical silicon tetrahedron types of minerals. We can kind of classify silicate minerals into two types, light-colored and dark-colored. The light-colored minerals are typically less dense, and one of those groups is called a feldspar. They have a three-dimensional network of tetrahedra. They're very, very commonly found, and there's typically two types of feldspars. One is called a potassium feldspar, which has a lot of potassium in it, obviously. The other is called a plagioclase feldspar, which has a lot of sodium and calcium in it. These are some pretty good pictures of those two types of feldspars. Quartz is a very, very common light silicate mineral, which has a three-dimensional network of tetrahedra. It's the second most abundant mineral and consists entirely of silicon and oxygen, but it may have impurities which can change the color of the mineral. So again, here are some good pictures showing those differences in color that all make quartz, but with different impurities. Some other minor light silicate minerals are minerals such as muscovite, which has excellent cleavage in one direction. There are clay minerals that are also arranged in tetrahedra, but arranged in sheets. And then there are the dark silicate minerals. They're dark in color and they have a higher specific gravity. In other words, they're more dense. And they're more dense because they usually contain more iron and magnesium. The first group is called the olivine group, which I showed you in an earlier slide, which we typically find in basalts from an oceanic crust, which is usually more dense than continental crust. And it makes up what we think is the mantle of the Earth. Then we have the pyroxene group, which again is found in basalt. Basalt is a dark-colored rock, so we're going to find pyroxenes in the basalt. And an amphibole group, which again is found in igneous rocks typically. And we also have some minerals which are possibly found nearer the surface. One is called biotite, which is a type of mica, like muscovite mica, but this is the dark colored variety of it, again contained in many igneous rocks. And garnet. Garnet is a highly crystalline mineral typically that is found in metamorphic rocks. So something has happened to some other type of rock, it has been changed under heat and pressure, and garnet is the result. And here are some examples of some dark silicate minerals. The one on the top of the slide is called augite, and at the bottom is hornblende, which is typically found in granites, but in very, very small quantities. Some non-silicate minerals are also in this chapter, things which are not part of a silicon tetrahedra type structure. Minerals which are considered carbonates, halides. Halide, a good example of a halide is rock salt or sodium chloride. Oxides, sulfides, sulfates, and of course native elements. A native element such as gold is considered a non-silicate mineral. And again, looking at the book, you can see these pictures and details much more closely. But again, just using the top example here, the carbonates, mostly consisting of calcite or dolomite, those are the mineral names. The chemical formula has some combination of calcium, carbon, and oxygen. And of course, we have economic uses of those minerals. And the best example of a carbonate is calcite, as you can see in the picture there. Sometimes clear, or most of the time clear, and having a property of double refraction. Then we have minerals which we want in some form to pull from the earth and use. We have what are called, of course, renewable resources. Corn, wind, water, solar, those are all considered renewable resources. And then we have the Earth's crust, where we have non-renewable resources. things like oil, aluminum, natural gas, coal. Not all of those are minerals or rocks, of course, but they are considered non-renewable resources. So we look at mineral resources as occurrence of useful minerals that could be extracted from the earth. Ore deposits are concentrations of metallic minerals that can be mined at a profit. So ore deposits are a little bit different from mineral resources, and you should remember that difference. And of course, economic factors can change and influence a resource. For example, gold 30, 35 years ago was very, very inexpensive. And so many gold mines closed down because it wasn't profitable to mine. Now, of course, it is much more profitable with the price of gold per ounce at a much higher tag. So we have minerals which might be extracted depending on the economy at the time. And last but not least, this is an example of the Bingham Canyon copper mine near Salt Lake City. As you can see, it's an open pit mine where copper ore is taken out from the Earth's crust, and of course the copper is extracted or taken out of the ore, the parent rock. So this is the kind of thing that we are doing to extract mineral resources from the Earth.